Hello everyone, welcome back to Random Matrix Theory. This is lecture 11. So the topic for today is solution of matrix models or matrix integrals. The method we'll be using is saddle point analysis. So now let's start with our partition function. In terms of eigenvalues can be written as you can write the partition function like this: product of n d lambda I to pi exponential n square by s of effective, s sub effective, and s sub, where s sub effective is this thing, t n. Notice that we have replaced the coupling by tnn, that is gs, by we have replaced gs by tnn less than j log of. Let me explain this first. Okay, so we have written the action in a different way. That is, first let me write how different it is. Replaced gs by using the expression t equals gsn, which, and 2, or let's use 1 and 2. 1 and 2. The second thing is, remember the Vandermonde determinant? The square of that is lambda I minus lambda j squared. Let's write something like this. It was something like this. So we took everything to the exponential, wrote it as a logarithm term, because if you see this term, the exponential of this term and n squared gets cancelled out, 2 goes to the power here, and exponential and log cancels out, so we have the Vandermonde determinant as before. That is, we recovered the previous action the previous partition function that we wrote in the last class. So this is how it's different. And the reason for writing in terms of the effective action is this. So as might be clear from the method we are going to use to solve it, that is the saddle point analysis, it uses the fact that we have done, or we are considering a saddle point, that is, we are extremizing our function, and this is done by the help of the effective action. S effective is the effective action. It's called the effective action. Yeah. So as n goes to infinity, the integral above, let me write it first, then I'll explain. The integral is dominated by a saddle point configuration that extremizes the action. That is, if you extremizes mean if you take a variation of the action, that if you vary the action around a certain point, you get, that is, the variation of the action is zero. The idea comes from something called Hamilton's principle. If you have done a bit of classical mechanics, you can look, or if you haven't done, you can just look it up. That is, the quantity action in classical mechanics is just the integration of L dt, where L is the Lagrangian, and it can be written as t minus v dt. And in classical mechanics, the Hamilton's principle states that the variation of the action or a particle, the path a particle will take, if you vary that path, it will always be the minimum. That is, the path taken by a particle will be such that this quantity that we call the action will always be minimized. It's a principle followed by every particle in the, yeah, it's a general principle that is followed by every particle in the universe. We don't exactly know why. I don't think there is a proof of the action why it's minimized, but it is minimized and it holds in every scenario. So that is the idea behind introducing the effective action. So if you want, you can search this up, action principle or Hamilton's principle, and you will just read the discussions, you'll understand where this idea is coming from. This is a physical or heuristic argument of what is happening here, or an intuitive idea of why the action must be minimized, because it's a general principle that is followed by every particle. That is, yeah, that's called the Hamilton's principle. So what we will do is vary with respect to eigenvalue lambda I. Since we are doing a variation, that is, we are taking the variation of the action, that is this thing, this should be 0. That is what the minimization or extremization of the action means. So if you take the variation, that is basically taking the derivative, if you take the derivative with respect to lambda I, you'll see you'll get something like this. That is this, the derivative of this, and since you're taking the derivative with respect to lambda I, any other w of lambda is 0, so only the lambda I survives, so you don't need to take the sum. And if you take the derivative of this term, it's just it's just the derivative of logarithm. It's just 1 over that, and so this is the expression you get if you take the variation or the derivative. We usually call this variation of the effective action with respect to a certain eigenvalue lambda I. So okay, for some of you, variation, or sometimes, or you can look up into something called calculus of variations, or you can search action minimization, anything you want, you can search it up and you'll notice a wide range of articles or pages, and you can understand what the minimization of the action is. Okay, so now since we are taking n goes to infinity limit, that is how we study these matrix models, the distribution of eigenvalues will be a continuous function. Previously, if it wasn't an infinite, n goes to infinite limit, so distribution is formally defined for finite n as delta of, this is how we define an eigenvalue distribution or a distribution like that. But since it's not finite, since we are taking n goes to infinite limit, we need to turn this into a continuous function. That is, this has to be a continuous function. Sorry, this has to be a continuous function, and one way to do that is just transform the summation into an integration. So let me write it in large n. This n goes to infinity. Distribution becomes continuous function also. Yeah, now let us do some assumptions here. First, assume rho lambda, that is our distribution, the eigenvalue distribution, vanishes outside an interval C. So, and it's those that vanishes outside an interval like this, they are called one cut matrix models. So we'll pick this assumption. Also, we'll pick another assumption while solving this problem. Also assume, for simplicity, that is the potential only has one minimum, and that is that 2 at x star. You can assume that we have, okay, since these are the two assumptions. That is, we assume that our rho of lambda, it vanishes outside the interval C, and these are called one-cut matrix models. And for simplicity, we also made an assumption, that is our potential W of x, or here it was W of lambda. It only has one minima, that is at x star, that is the minimum. Why we have done that? Because we can get some physical insights by considering, can get some physical insights by considering an effective potential, that is a potential term like this. If you consider it, log of, how did we get this effective potential term? It's just, if you remember the equation, from the equation, So from this equation, we took the 2t into that side and subtracted that, and yeah, that is, if you take the derivative of this effective potential, if you take the derivative of this effective potential with respect to, say, with respect to lambda I, you recovered this. That is it. For recovering this, okay, let me write it up. Yeah, so by that we have constructed a new function, that is the effective potential, which looks something like this, to get some physical insights into the problem. We want to understand what's happening at the level of the potential. If you want a physical insight of what's happening, we need to consider an effective potential. Why? How does that help us? I'll show that in a bit. So yeah, so we have considered an effective potential from this equation, that is, we get from taking the derivative of the effective action. And yeah, so this effective potential term offers us some physical insights into the problem. How is it so? First, there's in the effective potential there is a logarithmic term, and sometimes it's called the Coulomb repulsion term. So as I mentioned before, we are looking at it to get some physical insights of what is happening. So this logarithmic term is sort of like a repulsion term, Coulomb repulsion. Those of you who have done, almost all of you have done Coulomb repulsion in basic physics courses, that is the electromagnetic repulsion force. The Coulomb repulsion, it's sort of like a Coulomb repulsion in the sense that if the eigenvalues are close to one another, that is, the eigenvalues can't be the same. That is, if they are the same, this logarithmic term blows up. So if you're thinking of the eigenvalues as position of particles, you can't place two particles at the same point. That's a physical insight into what's happening. The logarithmic term, or it's sort of like a Coulomb repulsion term, even in matrix models it's called the Coulomb repulsion term. This prevents from having the same eigenvalue. That is, if lambda I equals lambda j, there is a divergence. You can't, if you think of it as particles, you can place if two particles at the same position, if lambda is at the position of particles. That's a physical insight of what's happening. Also, if you take a small t, if the 't Hooft parameter t is small, if the 't Hooft parameter is small, here this term dominates over the second term, right? So the potential term dominates over the Coulomb repulsion term, and if you think of them as particles, they tend to be at the minima. If you take, for example, if you take the derivative of the effective potential with respect to, say, it can be normal derivative, let's say partial. Yeah, partial is a better sign. So partial derivative with respect to x star, if they are with respect to x, this is 0. So x star, this term dominates, that is, this term dominates over this term, or more precisely, this term dominates over this term, because the 't Hooft parameter is very small. So in a sense that the particles tend to be or go close to the minima of the potential. If you think of it as a potential, even as you can think of the potential as a harmonic potential, that is like this, a squared potential like this. You can have squared potentials, and that is Gaussian potentials. You have dealt with this. So if you have a Gaussian potential, let me give you a physical insight. So since the particle tending to be at the minima is like it's trying to fall here. And if you say t equals 0, the particle is basically at 0, right? Sorry, at x star, that is at their minima. So this is a physical insight into what's happening. By taking the effective potential, we can have a intuitive picture of the eigenvalues. If we treat the eigenvalues as particles, we can understand what's going on. That is, two things are going on. The Coulomb repulsion, the sort of repulsion between the eigenvalues, they don't let the logarithmic term, in that sense, doesn't let eigenvalues to be the same, because the logarithmic divergence, log 0, is undefined. And if the 't Hooft parameter is small, we have the potential tends to be at the minimum. This is what happens. Now, if you remember, we considered an interval. Let's give it vanishes, that our rho lambda vanishes outside an interval. So think of it if the 't Hooft parameter t is 0, if the 't Hooft parameter is 0, this term is 0, there is only one minima, and the eigenvalues are distributed just at the minimum, right? The distribution of eigenvalues is just at x star. So the interval C, the eigenvalue distribution, collapses to x star. It's not an interval anymore, it's just a point. So the distribution of eigenvalues is just at that point. All of the eigenvalues are at that point. So there is no distribution, only one eigenvalue. So as t grows, that is, as you make t bigger, the Coulomb repulsion term will get stronger than our potential term, and it will repel eigenvalues to be apart from each other and to spread over an interval. That is, initially as t was 0, it was at this x star, but if you make t bigger, the Coulomb repulsion term dominates over the potential term, and the eigenvalues will move apart from the minima, and it will be the distribution will be, that is, the interval C will get bigger and it will be spread out. The interval C will be spread the interval C will get bigger in that sense. So the Coulomb repulsion will force the eigenvalues to be apart from each other and to spread out over an interval C. So this is what is happening as you make t bigger. This is what happening. This is why we considered the effective potential, so that we can get some physical insights, and we have successfully gathered some physical insights by taking different values of different limits of t and studying the minima of the potential and the interval, which is very important since the eigenvalue distribution is controlled by the interval. Okay. So now, since we will be studying n goes to infinity limit, that is, we'll be studying our matrix models in the case when n goes to infinity, that is, n is very, very large. So we have to make quantities continuous. Any quantity that is in the sense that if there is a summation, we'll replace it by an integration. That is how you make things continuous. Make quantities continuous. That is, if you have some, say, f of lambda I, now this becomes an integration over the interval C, f of lambda, rho of lambda, t of lambda. This is how you make things continuous. That is, you replace the summation by the integration and the density of your distribution. Also, distribution of eigenvalues rho of lambda satisfies normalization condition is normalized to 1. So all our equations will become continuous. So interesting thing is, what will happen to this equation? That is our favorite equation until now. What happens to this equation? We have to make a continuous version of this. So if we make this continuous version, so we'll have this is how p is just a constant factor, sometimes called the principal value of the integral, but yeah, this is how we made this thing continuous. That is a continuous version of this. Replace the sum by the integral, and since everything is controlled by the distribution, that is, the density function controls how at different places eigenvalues are spread out. So you have, since we are doing an integral, you have to always put in the density function. So now an interesting thing just happened. If you know the potential in terms of the eigenvalues, you can compute the rho of lambda, right? The density function of any matrix model by this equation. If you can find the density function, you can solve any quantities, right? So finding the density function is the ultimate goal of matrix models. If you can find the density functions, any quantity of interest can be found out by this. And this equation, which is an integral equation, this helps us find the density function from the potential. So in the rest of the part, we'll discuss a few more things. For example, once rho lambda is known, you can compute quantities like free energy and so on. So this is the ultimate goal. This is our golden duck. Also, now since we are making everything continuous, the effective action, if you want to write it in a continuous form, you can write it like this in terms of the density function. So effective action in the interval t of lambda, w of lambda, that is the first term, and the second term, since you have two eigenvalues in the second term, you need and I not equal to j, you need two different density functions for this scenario. And log of lambda minus lambda prime. This is how the effective action becomes. We won't need this much, but what we'll need is this equation. So for completion, I just wrote the effective action in terms of the density function. Also, similarly, we can compute averages or correlation functions in the matrix model. It can be computed as, there is trace of m to the l over the interval d lambda lambda l rho of lambda. So you can compute correlation function as well from this. This is the power of our distribution function. So if we know the distribution function, our job is done. In the next video, we'll talk about the distribution functions, that is the density function, density distribution function, and how we can solve it.